Welcome to this Building a Character Level Transformer course, where we will start from the beginning and build a character level transformer. You don't need any machine learning knowledge except Python knowledge. Let's first talk about hypothetical transformer that's made to predict names. We're gonna use this transformer to make it simpler. So this transformer is built only to come up with new names. So how would this work? The way this would work is you would give it a few names, and then it's going to try to predict the next character based on all of the previous characters. So if we are, for example, right here, it started saying JA, it sees all of these other characters, it's gonna say, okay, well, the next likely letter is M. And then it says JAM, then the next likely character is E. And it has a few likely characters that are more likely than other characters, and it's gonna choose one of those characters. And it's gonna, at the end, sound like a name. Let's see how this transformer would learn or train. Let's take a look at name Olivia, for example. When looking at this name, the transformer will learn that after big O, there is likely to come L. After all, there is likely to come I. And after Oli, there is likely to come V. So this is what the transformer would learn. It will also learn that beginning of the name, big O, is very likely to be at the beginning of the name, and also after Olivia, there is likely to be an end of sequence. And also, new lines are just treated as another character. Now let's train our small language model. We will start by downloading the data. We will use the tiny Shakespeare data. So I will show you what this data contains. So let's open it and read it. And after that, let's print the length of the data. So it has over 1 million characters. And we're gonna print the first 1,000 characters. And then you can see that this is just like a Shakespeare text. Now we come to the next step, data processing. We will make a list of all unique characters in the text. So the first step in training our model is to list all of the unique characters that we have. So we're gonna say character set is equal to make a set of text. This will return a set of unique characters in the text. So if we go ahead and print this character set, we're gonna see this set of unique characters. Then we're gonna say character list is equal to list character set. So this will convert this set into a Python list, which you can see here. This is just a Python list with same elements as this set. Then we're gonna sort this list. So it's going to be sorted after I print. This is gonna be sorted from exclamation mark to XYZ. And then the vocab size, it will be just the length of these sorted characters list. So it's gonna be 65. Now that we have a list of characters, we actually need to convert each or map each character to a number, because neural networks work with numbers. So we are going to map each character to a number in the following way. We're gonna say string to integer is equal to, and then we have some expression. So we have character mapping to integer for index, comma character in enumerated characters. So this is going to take this, this is a list of characters, and it's just going to take their index and map the index of the character to the character. So we're gonna get 0, 1, 2, 3, 4, 5, 6, 7, etc. And then we're gonna get exclamation mark, dollar sign, and sign, etc. So if we execute this and print this, we're gonna see that new line is mapped to 0, and then empty space mapped to 1, exclamation mark mapped to 2, etc. After that, we're going to create mapping from integers to characters. So this is so we can decode after our neural network spits an array of integers. We can decode them and convert them to characters. So integers to string is equal to, and then we just do the same, except now the key is integer and the value is character for index, comma character in enumerated characters. And if we print this, we can see that we have number 0 mapped as new line, number 1, etc. After that, we need to define a function that's going to get a string and convert it to a list of numbers. So we're defining it here. Encode is equal to lambda. We're going to define it as with lambda, and then this is the string that we receive. It's going to return some list. So string to characters of C, that is character, for character in string. So each character in string is going to be passed through this, and we're gonna get the integer, and we're gonna put the integer into the list of integers. So we will also define decoding function that's gonna convert list of integers to a string. So we are going to get in the list of integers, and then let's start from here. So for integer in list, we're going to just call this integer to string on that integer key, and it's going to return a character. So we're gonna make an array of characters, and then we're just gonna join them into one string. So let's see down what it looks like. Encoded result. So this is 40s, So if I have input string is equal to hi there, and I say encoded result is equal to encode input string, so it's gonna call this encode function, and then it's gonna say this is the hi there converted to integers, and then we're gonna call we have encoded result. We're gonna pass that through the decoder, and then we're gonna print the coded result. So this is the decoder. We're gonna pass it through, and it's gonna say hi there. Now we need to convert the entire Shakespeare text into a list of integers. We're gonna use that. We're gonna do that using a tensor. So tensor is basically same as array, but it can have any number of dimensions. So two-dimensional array is matrix. That's also two-dimensional tensor. Three-dimensional tensor, four-dimensional tensor, etc. So we're gonna import the torch. That's PyTorch, the machine learning library, and we're gonna say data is equal to torch.tensor. We are going to give in the encode. So this encode text is a Python list of integers, and then we're gonna say data type is torch.long. This is just 64-bit integer data type, and we're gonna basically convert this list of integers, Python list of integers, into torch tensor list of integers. If we execute this and we say print data.shape, so this is basically a one-dimensional array with million values, and then the data type is torch.int64, and then we're going to print the first 1,000 characters. Those are basically all of the letters converted to these integers. We're going to split data into 90% training data and 10% validation data. Then we're going to define block size equal to 8. Block size is basically the length of the block that we're going to use the number of previous characters to predict the next character. So after that, we're going to create two lists, X and Y. List X is going to we're just going to take the first block size characters from our data, and then Y is going to be from the second character to block size plus 1 characters. So what this is going to give us is these two tensors. X is this one and Y is this one. And as you can notice, 47, 56, 57, this is the same as this. So we're going to use this in the following way. We know that if we have character 18, then we have the target is 47. And if we have 14, 18, 47, target is 56. You can see it here. At times, we are going to feed just 1 or 2 or 3 characters into the neural network to predict the next character instead of feeding the full 8 characters. This is not only to save computing resources, but also, for example, in the beginning of the generation, it's going to only have 1 character, so it needs to learn that as well, those kind of situations as well. Now we're going to quickly learn about torch.randint. This will basically, torch.randint will generate characters from 0 to this number, so to 10, with this shape, 2, 3, 4. So here we have that situation. If we put 2 numbers as the first 2 properties, then it's going to generate integers with values between 4 inclusive and 16 exclusive with this shape. So we can see that right here. What's important to know is that you have a shape here, but if you want to generate one-dimensional tensor, then you need to use still a tuple with dimension, comma, and then empty. The PyTorch wants you to do it this way to keep the consistency of defining the shape. Now we're going to learn about torch.stack. So if we have two tensors and we use torch.stack, onto them the torch is just going to put both of them into one bigger tensor. And then if we use the same thing, we stack two of them, but with dimension 1, this will stack them by columns. So it's going to make a new tensor with 1 and 4, and then 2 and 5, etc. Next, we're going to define manual seed for reproducibility, and batch size is equal to 4, which is how many independent sequences will we process in parallel, and block size is equal to 8. What is the maximum context length for predictions? How many letters behind it's looking at to predict the next letter? Next, we're going to define this getBatch function, which will take in this variable split. So if split is equal to train, then we will assign train data to our data variable. Otherwise, we're going to assign validation data. So during the training, we assign train data, and now we need to pick 4 random characters in the entire data set. And from those 4 random characters, we're going to take the next 8 characters, or the next 7 characters, including that one. And then we're going to use that 8 characters to train to predict the next character. And we're going to do that at 4 random places in the data set. And we're going to get that by saying length of data minus block size. This is because we can get 4 characters from the beginning, but not completely to the end. There must be at least 8 characters at the end. So if we randomly choose the last one, there is still 7 more characters to get. And then the shape is going to be one-dimensional, and its batch size, which is 4. So as you can see right here, we have 4 random indices in that entire data, and below that we take, for example, this index, we find a character on that index, which is this character, and then the next 7 characters. So these are start at this index, and then on this index we have these characters, etc. And the way we get these characters at this index is, as you can see right here, we take torch.stack, and then from I to I plus block size for I in ix. Ix is just our entire ix is just this. And then for y, we're basically gonna have same as x, just one number later. So if this is 43 is second, then this is 43 is first. So we're gonna use, okay, so after 24, the next one is 43. After these two, the next one is this one, etc. And the way we will do y is right here. So we just go from I plus 1 to I plus block size plus 1 in data. And then this function is going to return x and y, which we will assign to xb and yb. And then in this for loop, we're going to loop through the batch. So there are four elements in this batch. And then we're going to also loop through each element one by one. So starting from 24, 43, etc. And then we're going to say context is equal to, and then we're going to create an array. The array is going to take the first t elements, whatever this t is, and then that's context, and then target is going to be write down in y the t number of elements. So this is 5. So this is, if we have these letters, we're gonna predict this one to be the next one. And then what this loop does is just does all of this, as you can see. Now we're gonna learn about nn.embedding. This is basically creating a lookup table where each of the indices has its corresponding array. The arrays are equal length, but this is also like same as matrix, where the first element is this array, second element is this array, etc. So basically we're gonna map each of our unique characters in our data to a vector, and these vectors are going to be saving the semantic meaning of this particular character. So the neural network is going to change these vectors to store the meaning. And so nn.embedding takes 2 parameters. Vocab size is basically the size of our unique characters, number of our characters, and the embedding dimension is basically like how many numbers each vector has. During the training, the neural network is going to adjust these values based on the loss calculated from forward and backward pass. Now let's learn a bit more. So logits are basically raw numbers that neural network produces. So if we are classifying between cats, dogs, and horses, the neural network is going to produce something like this: 2.1 for a cat, minus 0.5 for a dog, and 1.8 for a horse. So after that, we need to use softmax function to convert those to percentages. This is the formula for softmax function. So we take e to the 2.1, and then we divide that by sum of exponentials of all three, and then we get that this picture, for example, is a cat 55%. We get 0.05, 04 for the dog, and 41% for the horse. After that, we have cross entropy loss, which will basically compare the predicted probabilities with correct probabilities, and it will penalize the model for making mistakes and reward the model for making the probabilities as close as possible to the correct ones. Then we're gonna set the manual seed again, and we are going to define a class bigram language model. This is not a transformer, but this is a very simple language model that we will do first. It predicts the next character based on the previous character. Now we're going to initiate bigram language model. We're gonna say m equal bigram language model, and then we're gonna pass in vocab size. Now this is gonna receive vocab size and create embeddings. Now you may wonder why are we passing vocab size and not the actual vocabulary? This is because in our vocabulary we have indices from 0 to the number of characters. Each character is mapped to a like an integer, and then here in embeddings it's also going to create embeddings from 0 to vocab size. Is going to map all of them to vectors. So when we say logits comma loss is equal to m, and then we pass in xb and yb, and now remember that xb and yb are basically these x and y, they are the same, so xb and yb, and then it's gonna call this forward function. So forward is receiving idx, which is basically our xb, which is a tensor of all of these 8 characters, 8, 8, 8, and then we have target, which is yb, which is basically tensor of the next characters that need to be predicted. After that, this is very important. So now we're going to define logits, which will be, what we will do is we will pass in our xb tensor, and we are going to, for each of these integers, we're going to look at our embeddings and replace each of these integers with the corresponding vector that we just generated in embeddings, as I just explained. This will give us a tensor of b times t times c. So we're going to get b, this is number of batches, 4 times t, which is t is 8 characters, and then each of them is going to have c like a vector that corresponds to these integers. After that, we have an if statement. So if target is none, then loss is none. This means if we are not training but we are generating the letters, then we're not going to have any targets. But otherwise, if we are training, it's going to execute this. First thing we will do is extract shape from logits.shape into batches, time, and channels. And then we're going to reshape it so that it can be received by cross entropy. So what we will do is just multiply batches times channels. So the first dimension is going to be 4 times 8, 32. So instead of having like this in 2 array of arrays, we're just going to put everything into 1. And then each of these is going to have a channel number of, so each of these is going to be a vector with channel number of values. So after we reshape these two, we're going to call loss is equal to f dot cross entropy, and then we're going to calculate the difference between our logits and targets. And then we're going to return logits and loss. And here we're going to print logits.shape, which is 32 and 65. And then we're going to print loss in this example of 4.8, etc. So let's take a look at this generate function. So it's going to receive an array of integers, which are our characters that we represent with integers, and max new tokens, the amount of tokens you want to generate, amount of characters. And then we're gonna go through to the max new tokens number, and then we're gonna say logits.loss, comma loss is equal to self.idx. This will call this forward function. It's gonna pass in the array of characters, and target is going to be none. So here, logits, this will basically take this array of characters or array of integers, and it's going to replace each integer with the corresponding vector, our embedded vector. And then those will be logits, and then because target is none, loss will be none. So right here, we're gonna get logits and loss will be none. And then we actually, just in this model, we actually just want to look at the last character, the last one. We don't want to look at previous. We're gonna look at the previous models later in this tutorial. So we're just gonna say we're gonna keep the batches, and we're gonna remove all of the characters before the last one. Just keep the last one, and then we're gonna also keep channels. So after that, we're gonna just get probabilities. So that character, what are the probabilities for each of the possible characters and each probability? And then we're gonna sample from that probability distribution, and we are going to just concatenate that character to our string that we already have. So right down below, we are actually going to generate the letters right now. So we're gonna start by passing tensor of 1 by 1 of 0, so 1 0 in a tensor, and which d type is equal to torch.long, and then we're gonna call this generate function with max new tokens equal to 100. Generate function is going to return 4 batches, like 4 generations, and that's why we're just gonna take the first one with index 0, and we are going to convert that from a tensor to a Python list, and then we're gonna call decode function to convert those integers into our letters, and this is what we got right now. So as you can see, it's random letters because we have not trained it properly. We just did like a little bit of like showing. Now let us actually train. So first we're gonna define our optimizer, which we will use Adam W. Then we're gonna define batch size to 32 instead of 4, so it trains faster, and number of steps 1000. If I run this, it's gonna go for 1000 steps. It's gonna define get batch with train. Then we have logit slots optimizer, loss.backward, and optimizer step. At the end, we're going to print the loss. So training has completed, and this is our loss. It doesn't mean anything to you, but let's generate characters. And right now it's still looking at just one previous character, but it's going to actually look like Shakespeare a lot more. And we can see that it actually has even some words, to be honest. Now let's learn a bit of mathematics. So if you have 8 characters, what is the best kind of way, when you are predicting the next character, what is the best way to kind of store this information, like the meaning of these 8 characters? When one of the ways, not the best, but the quickest and simplest, is to just take the average. So 8 characters, each of them represented by an integer, you take average. That average is going to represent some kind of meaning, so you can predict the next character. Okay, so how do we take average? As I said, each character is represented with a vector. So let's take a look at this tensor right here. So the first character is represented with this vector, second this one, this one. So if we want to, the first character, we take an average of this, it's going to be the same numbers. Okay, the second character, so the second character, we have 4 and 5.5. So average of 6 and 2 is 4, and average of 4 and 7 is 5.5. And then for the last character, we take average of 2, 6, 6. Average is this one, and then, you know. Now if we take a look at this tensor, you can see that this is triangular matrix. So the upper triangle, all zeros. And then we have some numbers below. So you can see that the first row, every row adds up to 1. So the first row, 1 plus 0 plus 0, 0.5 plus 0.5 plus 0, every row is 1. So it turns out, if you do a matrix multiplication between this matrix and this matrix, you get this matrix, and I will explain how. So we can use these to get averages easily. So we multiply the first row 1 times 2, and then 0 times 6 plus 0 times 6, the dot product. You get 2. Then the dot product again, so 1 times 7 plus 0 times 4 plus 0, this is 7. Okay, let's see the next row, dot product between this and this column. So 0.5 plus 2 times 2, and then 0.5 times 6, and then 0 times 6. So you can see that we have 2 numbers, and we are multiplying both with 0.5. And then when we add up them, it's going to be same as adding the two numbers first and then dividing everything by 3. So if you didn't get that, let's see the third one. We have 3 numbers. So how would you find average of 3 numbers? You say number 1 plus number 2 plus number 3 and divide by 3. Or you can just multiply number 1, divide number 1 with 3, number 2 with 3, and number 3 with 3, and then add the results. That's what we are doing here. This vector dot product with this column, and we type it here. And then this dot product with this, we type it here. And now, how do we get this matrix? So we're gonna start with a matrix of all ones, and then we're just gonna turn the upper triangle to 0, so we get something like this. And then we're going to just take each row and divide it by the sum. So each number in each row we're gonna divide by the sum of that row. I added this comment that explains it even better. And then C is equal to A at B. This is matrix multiplication, so we're just gonna matrix multiply A and B to get the tensor of averages. Now let's take a look at the following example. So we have a manual seed for randomness, and then BTC dimensions are 4, 8, 2. Now just to remind you, so T is each character. We have a sequence of 8 characters right here. We want to predict the next one. B for batch is we have 4 examples of those 4 characters, independent examples. And then C is each character is represented by a vector of values. So the dimension of that vector of values, it's 2 in this case. We're gonna initiate all the values to be random. And now we are going to create a XBOW tensor of BTC dimensions and fill it with zeros. And then we're gonna go through each batch, and then we're gonna go through each letter. Through each letter, and we're gonna create XPrev tensor. So what we will do is create an array or a tensor for this current batch, going from the first letter to this current letter. So because t plus 1 is excluding t plus 1. So to the current letter we're going to create an array. This will be times, so this will be basically all of the characters times each character represented by a vector. And then we will create a new tensor, and at the coordinates batch and character we're going to set the mean of this XPrev, which contains all of the previous letters in that batch to that specific letter. And now we will just do the same thing. So we will create the triangle of ones. So the V is a triangle of ones. You can see it right here, the triangle of these values. And then we're actually just gonna create a new variable xbow2, and we're gonna multiply way with our tensor x. This is the explanation. So it's going to go through each batch and multiply t by t with t times c, t by c, and it's going to get btc. So this is it. And then we're just going to check if xbow, our previously defined xbow that I showed in previous example, is exactly the same as xbow2, and it is, which we can see with this true. Okay, so next we're going to use softmax to do some trickery. So first we're gonna define this trill variable, which will basically be a lower triangle of ones, and then we will make a weight matrix, fill it with zeros, and then we're gonna mask all of the upper triangle with minus infinity. This is because we don't want the tokens to look at the following tokens. We don't want characters to know about following characters when deciding the next character. When deciding the next character, we only want to look at the previous ones. We don't want to know anything about the following. So that's why we put their weight to minus infinity. But this is very ugly kind of distribution. So we are actually going to use a softmax, and then weights after softmax are actually a lot prettier. They sum up to one up until before the token that we are investigating, and they are 0 after. And so at the end, we are going to matrix multiply the weights and our X matrix, which is our original matrix of our tokens. And then we are going to get something like this. These are weighted tokens. And now let's talk about self-attention. So we're going to define X tensor, which is B times T times C. And then we need to understand the following. Each token has key, query, and value. So when you are generating next token, the key is describing what this token contains, what information it contains, what it contains. And then query is what am I looking for? So query is sent by the last token to each tokens, describing what the token is looking for. And then query and keys. This query is multiplied with each key. And the higher the similarity, the more weight there is. So the more importance there is on that particular token. And keys, queries, and values are all tensors. And when we multiply them, we perform tensor or matrix multiplication, for example. And so whenever we multiply key and query, we get weight of importance of relationship between those two tokens, and then the value is what gets, so the information that this previous token stores that's being sent. So key is like description of what it does, and value is like what it's sending, what it's communicating to the next token that we are generating. So we're going to define key, query, and value as linear elements with input size 32, this is channels, and then output size is head size, which is 16. And then we're going to pass our tensor of tokens X through key and query. And then we are going to matrix multiply all of the keys with this specific query. And then we are so because this is B times T times 16, we cannot just multiply this and this. We need to transpose K. We need to switch these two. So we have B times T times 16 multiplied by B times 16 times T. And the way we're going to switch these two in query is we're just going to transpose the second to last with the last. We're going to get B times T times T. So this way is storing the weights, the importance of each token. And then after that, we're just going to do this kind of transformation. So we get nice weight numbers. And then we're actually going to create our values for our X. We could have created values here as well. It doesn't matter. But we have our values for our X tensor. And we will just say out is equal to weight matrix multiplied with values. So values is what the token is communicating to us, but then what is the importance of each token? The way determines the importance of each token, so that's how we get the output. And the shape of the output is 4 times 8 times 16, which is head size here. And at the end, this is the full finished code. You can just press play, let it train. You can determine the number of steps right here, 2000, train for more steps to get better results. And let's see how it works. It works like this. So this is a semi-decent Shakespeare generations. Obviously, this is very simple model. If we improve the model, it would be better. That was a course for creating a simple GPT. Hope you enjoyed, and thank you for watching.